So the reason why I'm starting back at this particular slide is because this particular slide talks about the relationship between the cell potential and Q in non-standard state conditions. And one of the things that's important to understand about that is it gets us to the point where we talk about the Nernst equation. And so the Nernst equation gives us the fact of the matter is that the cell potential, the non-standard cell potential equals the cell potential minus RT over number of moles, Faraday constant, natural log of Q. Now, since delta G and cell potential or change in free energy and cell potential are proportional, you can substitute and rearrange to get this basic, not basic, but we call this the Nernst equation. And as a result of this being the Nernst equation, there are a couple of different variations of said Nernst equation. So for example, one of the variations of the Nernst equation is this one right here, which is one that we're going to spend some time with today. And the 0.0591 is a value that you get when you multiply the ideal gas law constant times temperature divided by Faraday's constant. So that's a value that you don't necessarily have to memorize, but it is kind of a shortcut for in the future. Also, other things to consider or to remember rather is the fact that even though they give you the Nernst equation in some way, shape, or form on the AP exam, it's not a huge focus of your math. It's more likely along the lines of your ability to understand the relationship, for example, between Q and K, or change in free energy and cell potential. And so this will help us to get there. Now, this interrelationship of change in free energy, the cell potential at equilibrium constant, this chart right here is a chart that you're probably going to want to memorize. And again, these sets of formulas over here allow us to go from the cell potential to the equilibrium constant, or the equilibrium constant to change in free energy, or change in free energy to the cell potential. All of these are equations that could be used, but we don't need to spend a lot of, we're going to do one or two examples with them. You're going to have a couple for homework, but beyond that, it's more important that you know the relationship between these two things. So for example, the cell potential, and if the cell potential is greater than 0, that means that the change in free energy is less than 0, and that means that the equilibrium constant has to be greater than 1. That would tell us that the reaction is thermodynamically favored. If the cell potential and the free energy are equal to 0, and the equilibrium constant is a value of 1, you are at equilibrium. We also refer to that on Friday as that would be a dead battery, for lack of a better term. And lastly, if your cell potential is less than 0, and change in free energy is greater than 0, and equilibrium constant is less than 1, then the reaction is not favored as it's written. So that is something that you have to really kind of think about or keep in your memory, for lack of a better term. Now, is that we determined that the cell potential that we calculated was positive, right? So that means it's greater than 0, which meant that K, when you calculate it out, also ended up being greater than 0. And that's an important distinction, and that tells us that this reaction is thermodynamically favored at standard state conditions. So really, for when we're working with these types of reactions, it's more important that if it's asking you the interrelationship or talks about how equilibrium constant comes into play with this stuff here, this is the idea that we have to understand more than the Nernst equation itself. You guys don't have to understand Nernst equation, what we just worked through, but you do need to understand the relationships, if that makes sense. So there are a couple of slides that I skipped, the ones where we had Q is greater than K and Q is greater than K and Q is greater than the cell potential, or Q is less than the cell potential. You need to keep those in mind as well, because that's going to help us answer a couple of the questions in the future for today's lesson. So we did not talk about this. I don't think we started this problem on Friday, So we're going to talk about this today. So the very, very first thing I'm going to do is I'm going to try to identify what's going on in terms of what's being oxidized and reduced. So we have tin with a 0, tin with a +2. So it looks like it has lost electrons. So in this case, tin is oxidizing. Copper is a +2, and it goes to, sorry, not a 0, it goes to a +1. So that appears to have lost or gained electrons rather. So copper in this case is reducing. Okay. So when I go to write the half reactions, I'm going to have this and in the case of copper, I would probably write something like this out of the textbook, out of Appendix E. However, because the equation has the formula or the net ionic equation has a coefficient of 2 here, that tells me that really there were 2 sets or moles of electrons being transferred. So really I have 2 Cu plus 2 plus 1, or not 1, plus 2 electrons, making 2 Cu plus 1, so that it matches the balanced chemical equation above. Now, the reduction potential for the tin half reaction is negative 0.136 volts, and the half reaction for the the half reaction reduction potential for the copper is positive 0.153 volts. And because the cell potential or cell reductions are intrinsic properties, it doesn't matter how much stuff is present, the cell potential or the reduction potential is going to stay the same even after we multiply it. Yes?
Why would we add both of them together for the same thing?
Say that one more time.
Why are we adding the Cu plus 2 plus 1 electron with the 2 Cu plus 2 plus 2 electrons?
We're not adding. This here, this positive sign, that plus is not addition. That is the convention of the voltage. So it's positive volt potential or cell reduction potential. And even though I multiplied the half reaction by 2, because that's the amount of moles of electrons, we'll talk about that in a second, it doesn't change the cell reduction potential. Okay? So the other thing that we're getting at here is that the number of electrons, according to the half reactions that are being transferred in total, are 2. But we know that coefficients in chemical equations are really telling us the number of moles. So in this regard, what we're really talking about is that the number of moles that are present in this reaction is 2 moles of electrons. And that's going to be important in a minute. Okay, so we'll come back to that. Now, the first thing I'm going to do is I'm going to go ahead and I'm going to calculate the cell potential. So in this case, I'm going to calculate the cell potential by using the formula. The standard cell potential is equal to standard reduction potential minus the standard reduction potential for the oxidizer. And so in this case, the cell potential will equal the positive 0.153 volts minus the negative 0.136 volts. And that will give me my cell potential to be positive 0.289 volts. Okay. So with that in mind, and this understanding that there's 2 moles of electrons here, this is asking me to calculate the equilibrium constant. And so what I'm going to do is I'm going to go ahead and use the formula up above, and I've manipulated a little bit. So the E cell potential will equal the 0.0592 volts over N times the natural log of K. So when I plug in my cell potential value, and when I eventually solve for my equilibrium constant, I get something like 5.8 times 10 to the 9th for my K value. Yeah. The number of the moles of electrons that were transferred from tin to copper. Okay. Yes?
And you just multiply by 2 to make sure the electrons are the same in each?
Yes. Okay. Now, in this problem here, the really thing that's important to understand, in this example, if I was to go ahead and write the half reaction for what's going on here, I would say that I would have the zinc and I would have the hydrogen okay? And in this particular case, we would understand that hopefully by looking at the zinc one, zinc goes from a 0 to a +2, and the hydrogen goes from a +1 to a 0. So that should tell me that the zinc is oxidizing and the hydrogen is reducing. Okay? So if I'm thinking about like a system in terms of which side would the cathode, or where would the zinc be? Would the zinc be on the cathode or the anode side? If I said this is my anode side, which thing, the oxidized or the reducing, goes to the anode? Oxidizing. So over here, I would have a zinc anode, which would mean that over here, I'm going to have some H2 being produced at the cathode. And one of the things that we have to keep in mind is that we are now using the voltaic cell, using the following reaction, and we are going to talk a little bit about how Q applies to that. So we have to go back to the notes and think about how Q applies to this. So remember, Q is at initial conditions, right? And K is at equilibrium. So we're going to talk about how if predict the following changes, how these changes will have on cell voltage. So we're going to look back at those notes and in terms, or the slides where we talk about how Q is comparable to cell potential. So in this case, if we increase the pressure of the gas, of the hydrogen gas, is increased at the cathode department. So that means what will happen to Q there? If I increase, so if I have Q and I increase the pressure of the hydrogen gas, that means that Q is going to go up. Which will mean what about the cell potential? Think about Le Chatelier's principle.
Down.
Yeah, it will go down. Okay. So in the case of B, zinc nitrate solution is added to the anode department. Concentration, or well, the Q quotient or the Q ratio will go up because we're adding more zinc, right? So what's going to happen to the equilibrium, or not the equilibrium, what's going to happen to the cell potential?
Down.
Should go down as well. So if I add sodium hydroxide to the cathode compartment, so remember the sodium hydroxide would be, so this would be my cathode side. So if I add sodium hydroxide here, what's going to happen to Q? Q will go up. What's going to happen to E?
Go down.
It'll go down again. Yes, sir.
Why is the QG going up?
In this case, we're talking, like, thinking about the Chatelier's principle. And so in the case of this, like, in the case of adding, like in the case of sodium hydroxide, the sodium hydroxide is going to, the Na is not going to do anything, but the hydroxide could potentially react with the hydrogen to create more H plus.
Okay,
Okay,
okay.
and then as a result of that, the cell potential will go down. So like that's kind of how I'm looking at it. That's the litmus test. So what I'm adding is what is it doing to the Q at the beginning.
So, if it gets more acidic, Q goes up, or if it gets more basic on the anode side, it goes up?
Yeah. And then what happens if we double the surface area of the anode? Yeah, there's no effect on cell potential, or yeah, cell potential. Because again, cell potential is intrinsic, which means that it doesn't depend on the amount of stuff that's present. It's just gonna be no matter what. K. Not literally K, but K. What? Well, those, yeah. I'll come back to the homework. Let me just finish going through this and I'll make sure you see the homework problem. So, the electrolysis of water.
Can you go back to the director on the homework?
Okay. So, the electrolysis of water, just pay attention to what's going on here first. Okay, I don't know that you have to write a lot down for this particular slide. But in this case here, the overall cell reaction says that if I take liquid water, I'm going to produce hydrogen gas and oxygen gas. And technically speaking, the ratio of hydrogen gas to oxygen gas is going to be 2 to 1, especially when we balance that out. Now, the oxidation half reaction here for the water, so there's two different reactions that are going to occur. First of all, I should probably tell you guys that in both of these test tubes, the anode and the cathode are inert. So they're either like platinum or they're carbon or they're graphite or something along those lines. So there's nothing's really forming, like they're not going to get, the mass of the cathode and the anode are not going to get larger. But what you do need to know is that if I take liquid water and I electrolyze it, that is I add electric current to it, I'm going to produce some oxygen. And if I reduce water, I'm going to produce some hydrogen at a rate of 2 to 1. So when we electrolyze water with inert electrodes, what ends up happening is that we produce gas, hydrogen gas and oxygen gas at a rate of 2 moles of hydrogen gas for every 1 mole of oxygen gas. Electrolysis reactions are different than voltaic reactions in that we have to add electric current for them to happen. So like this reaction is going to happen, but it needs electric current in order for it to happen. And as a result of that, when we talk about an electrolytic cell, which I'm going to go to the next slide, electrolytic cells take non-spontaneous reactions and make them occur when we apply electricity to supply the electrons. So for example, the aluminum ion, when we electrolyze aluminum in some way, shape, or form, we have to generally, it requires negative 1.66 volts for the cell potential. What I'm getting at here is that in order for this to occur, we have to go ahead and add current. So the difference between this cell and the voltaic cell that we spent a lot of time on is that the electrolytic cell requires a power source or a power supply instead of a voltmeter. The power supply is making the electrodes flow, or the electrons flow. Note, the signs of the anodes and the anode and the cathode in this case are different than the voltaic cell. In this case, the electrons are flowing from positive to negative. In the voltaic cell, it's the opposite. I'm going to show you a slide that's going to be kind of important in a second. just so you guys are aware, at one point in the history of the world, the production of aluminum was so complicated, it's gotten significantly easier now, that aluminum was more of a precious metal than gold, silver, or platinum. It was so much of a precious metal that the very, very, very top of the Washington Monument is not stone or brick. It is a solid pyramid of aluminum, because at that point in time, that was the most precious metal on the face of the planet, in large part because it required so much electricity to make it, it was almost useless to make. And now we just throw aluminum away. Okay, because it's only worth like 10 cents. I know, but people just.
That's your get-rich-quick scheme. If you like invent a time machine, you just bring back a bunch of aluminum.
I guess. We'll have to consult Bill and Ted's Excellent Adventure 3 on that, because that's coming out. Now,
I know, but it's still-
here's where we're at. This slide right here is basically showing you that a voltaic cell, all of the information that you've been told to memorize about the voltaic cell is the exact opposite for an electrolytic cell. So if the change in free energy is less than zero, hang on, then the cell potential will be more than zero, and the anode will have the oxidation process at it, and it'll be negative. But if an electrolytic cell, if the cell potential is greater than zero, the change in free energy is greater than zero, the cell potential will be less than zero, and the anode is where oxidizing is occurring, sign will be positive. So I think you should probably write this down. I'll give you a few seconds to do that. I just wanted to explain it. So I'm going to wait here while some of you write this down. Now, just hold on. Faraday's law of electrolysis says the amount of a substance produced at the electrode is directly proportional to the amount of charge flowing through the cell. Essentially what that means is that if I want to make something like 12 grams of a product, I need to create 12 times that amount, so 144 amps of current or something like that. Does that make sense? So it's inversely proportional. What I'm getting at here is that 1 amp is equal to 1 coulomb per second, because the measure of charge per unit of time is the amp. That can be manipulated in a couple of different ways. So for example, 1 coulomb would be equal to 1 amp second, right? And if we use the Faraday constant that says 96,500 coulombs per moles of electron, we can relate coulombs to moles of electrons, and the redox half reaction will allow us to find moles of electrons, and then we can use some sweet dimensional analysis to help us solve a couple of Faraday law problems, which isn't too bad. So we're gonna walk through a couple of these problems. They're good, clean family fun. This one and one more. Well, I believe before we started this, I said there. All right, now, the electrolysis of molten magnesium chloride is the final step in isolating magnesium from the seawater. Calculate the following for the reaction, in which case you are trying to get 45.6 grams of magnesium. So remember, there's the inverse relationship between the amount of coulombs versus the amount of product it formed. But because we're talking about the electrolysis of magnesium, the half reaction in question here is the magnesium half reaction. So we're really concerned about the fact that magnesium is that particular half reaction right there. Now, I don't have to go back into the textbook and look into Appendix E and look for the cell reduction potential here, because I don't need it for this particular style of question. What I'm going to do is I'm going to use some sweet stoichiometry, like 45.6 grams of magnesium I'm going to first convert that to moles of magnesium. Okay? And then what I'm going to do is I'm going to realize that in 1 mole of magnesium, I have 2 moles of electrons, which I'm going to rewrite as 2 moles, not 2 moles, as 2 Faraday. Okay? So my 2 moles of electrons equals 2 Faraday, or 2 times Faraday. And so if I really want to figure out what the relationship then says, is that 1 Faraday is equal to 96,500 coulombs, because that's what we learned the other day. So when I plug this into the magic calculator box, I get something like 362,000 coulombs. So that is definitely an inverse relationship. I need to pump in 360,000 coulombs of electric current to get 45 grams of magnesium. That seems like a lot of energy to get like some magnesium, I guess. So I guess the question is, how many amps are needed to do this if we can get the 45.6 grams in 3.5 hours? 3.5 hours, people. That's a long time to get 45 grams of magnesium. I feel like this is not the most efficient use of our time. Yes, ma'am.
Wait, what is this 2
It's 2 moles of electrons in 1 mole of magnesium, right? But I said that the 2 moles is really equal to 2 times the value of Faraday, or 2 Faraday. But the real reality is that 1 Faraday is equal to 96,500 coulombs. So, in part B, we're going to calculate the number of amps. So I have 45.6 grams of magnesium is being produced. We know that 1 mole of magnesium will equal 24.31 grams of magnesium. We know that the 2 Faraday equal 1 mole times the 96,500 coulombs in 1 Faraday. Now, here's where things get a little bit, not tricky, but convenient. That conversion that I showed that said that like a coulomb is equal to 1 amp times seconds. Remember that in the last slide? I'm going to use that guy right now. So I'm going to convert coulombs to amp seconds. And then I'm going to convert seconds. So I'm going to take I'm going to say that I have 60 seconds in 1 minute, and 60 minutes in 1 hour. And I'm going to take 1 over the 3.50 hours that is required to produce this, which will give me a total of 28.8 amps, which again is kind of a lot, of considering the fact that I believe we said earlier this time around that your cell phone is like a 0.2 amp or something like that. So